So what I'd like to do now is relate molecular orbital theory back to some of the qualitative ideas of bonding that were discussed in the previous unit. And the analogy that I want to use here is to consider atomic and molecular orbitals essentially as homes for electrons. So now if we think about an orbital energy diagram, we could consider a pair of atomic orbitals that we're going to mix and use to form molecular orbitals. And in this analogy of these orbitals being homes for electrons, let's just make them one-bedroom apartments. Okay, so your friend has a one-bedroom apartment, you have a one-bedroom apartment, and then if the two of you were to move in together, you would have enough stuff to demand a pair of bedrooms, right? So now a two-bedroom apartment. Okay. The analogy here is to think about what these new bedrooms look like and how habitable they are, how much you'd like to spend time there. Right? And so in order for this to work, the idea is that you've got a bunch of stuff in your room, your friend's got a bunch of stuff in his room, and when you move in together, the first thing you do is you see what stuff goes together. So you take the bed out of your room, the nice chair out of his room or her room. You take, maybe the plasma TV from one and the really nice stereo system from another, and all of that goes into a room where everything goes together, right? So you get one really good room and then one room where everything that didn't go together is kind of thrown into, right? So you've got a good room and a bad room. Of course, in the context of orbitals, good and bad really correspond to energy, right? So low energy is a good room or a good orbital, more favorable orbital, and then the less favorable room is higher in energy. Okay, so now in the scenario where you were in your apartment, your friend was in his or her apartment, when you are thinking about whether or not to move into a two-bedroom apartment together, you want to think about, well, how nice will it be to live there? Okay, now you're both electrons, which means that two of you are very happy to share a room together. And so in this scenario, the two of you, you're electrons, so you obey the off-bow principle. You both spend all of your time in the good room where all the cool stuff went, right? You're both much happier than you were before. If, on the other hand, your friend had an electron roommate, then when everybody moved into the new two-bedroom apartment, one of you gets left out of the good room, right? This, of course, would be your friend's roommate, and ends up in the not-so-good room. When considering whether or not to make this move, you take a vote. Two of you are much happier, one of you is much less happy, so the two of you win, and you end up in this new two-bedroom apartment. It's still a bonding arrangement, but it's not as favorable, right? Of course, if you also had a roommate initially, then when everybody moves into the new place, two people are happier, two electrons are happier, two electrons are less happy, and the net effect of that is that there's not enough momentum to carry you guys into making the decision to move into the new room. So that's sort of the classical picture of bonding versus anti-bonding electrons and deciding the bond order of a new molecular orbital arrangement. Okay, but the piece of this analogy that I want to stress here is, what did those new rooms look like in the apartment? And in the picture here, the original bedrooms and the one-bedroom apartments, right, were equal in energy. They were, an analogy, degenerate atomic orbitals. Okay, and what that means is that in the new cool room, that's kind of got half of its stuff from your apartment and half of its stuff from your friend's apartment, and the same for the really bad room. Okay, so the new molecular bonding orbital here, and in fact the anti-bonding orbital as well, looks like an equal mix of the two degenerate atomic orbitals. And so what this corresponds to is a picture of what you would refer to as being a purely covalent bond. The electron density is evenly distributed around the two nuclei that are responsible for forming that bond. Okay. So let's consider what happens now if the two atomic orbitals weren't identical in energy to begin with. One of them was a little bit lower than the other. In other words, one of the bedrooms initially had better stuff than the other, right? It was an orbital, it was a home in which you'd rather spend more of your time. Okay, so now here, your one-bedroom apartment was a little bit cooler than your friend's, and when you guys combine, well, you do the same thing, right? All the really good stuff that goes together goes into one of the rooms, and everything that's left behind goes into the other. So you've still got a room that's better than your one-bedroom apartment was to begin with, but not as much better, right? You only got 30% of the stuff from your new roommate instead of half the stuff. So this corresponds to less mixing between the orbitals, right? There's less orbital splitting for the new bonding molecular orbital relative to the energy of the atomic orbital in which you began. Okay, now it's still net favorable for you and your friend, and so should we start that over?
No, I can just cut it out because as soon as you come with a new...
Start with it's still net favorable?
Okay,
Yes.
all right. Okay. So it's still, that's fine. So it's still net favorable for the two of you, right? When you move in, there are now two of you that are inhabiting a room that's better than what either of you had before. But this new room now, it looks more like your old apartment than it does your friend's old apartment. And so this is, by analogy, what a polar covalent bond looks like, right? The new molecular orbital corresponding to the bonding orbital looks more like the old better atomic orbital. In other words, the orbital that was on what was originally the more electronegative atom, right? The place where the electron was lower in energy was happier. Okay. You can take this analogy even further and push it to the extreme, where one of you just had a great apartment and the other one's was pretty lousy to begin with. Okay. And now, when you guys combine all your stuff and move together, you still get a pair of molecular orbitals. But the cool room just has all the stuff that used to be in your apartment, right? Your stuff's a lot better than your friend's, and the lousy room pretty much looks like your friend's old apartment. What this means, in effect, is that it's like your friend is now spending all of his or her time in what used to be your apartment. Your friend is essentially transferred where he is, his electron density, from his apartment to yours. And this is an ionic bond, right? You can think about this as being the transfer of electron density from one nucleus to the other. And so the picture to come away with out of this admittedly somewhat goofy analogy is to think about this continuum of qualitative bonding, of purely covalent to polar covalent to ionic bonding, and realize that it corresponds to very specific pictures from molecular orbital theory and the molecular orbital view of what bonding in molecules looks like.